For a few evenings just after sunset, there will be a planet hiding in the orange light. Most people will not notice it. They will see the bright sky fading. They may see Venus if it is there, brilliant enough to look almost artificial. They may see Jupiter, steady and pale, holding itself above the horizon. But lower down, closer to the place where the sun has disappeared, there may be a smaller point of light that looks too fragile to matter. That point is Mercury. It is the closest planet to the sun. It is the smallest planet in the solar system. It is a world made of stone and metal, baked by sunlight, frozen in shadow, scarred by impacts and pulled so hard by the sun that even its orbit once seemed to disobey the laws of physics. And yet from Earth, Mercury behaves like a secret. It never climbs high into the midnight sky. It never shines all night like Mars or Jupiter. It does not dominate the evening the way Venus can. It appears briefly in twilight, close to the horizon, almost always half lost in glare. Then it vanishes again. On June 15, 2026, Mercury reaches what astronomers call greatest eastern elongation. The phrase sounds technical, but the idea is simple. From our point of view on Earth, Mercury will appear as far east of the sun as it can during this part of its orbit. That means it becomes one of the better evening targets of the year. Not easy, never easy, but possible. For a short time after sunset, if the horizon is clear and the sky is kind, Mercury can be seen with the naked eye. That sentence sounds ordinary until you remember what it means. You are looking toward the inner solar system. You are looking into the region between Earth and the sun. You are seeing a planet that spends most of its life drowned in daylight, from our perspective. You are seeing a world close enough to be part of our planetary neighborhood, yet hidden so well that many people who love the night sky have never knowingly seen it. This is dark matter radio, and tonight we are following the planet that hides in the sun's glare. Mercury is often treated like a footnote. The first planet, the smallest planet, the quick one, the little gray dot before Venus, but it deserves a stranger reputation, because Mercury is not merely close to the sun. It is trapped in a difficult geometry. To understand why Mercury is so elusive, start with a streetlight at dusk. Imagine standing on a road while a small reflective object sits near the lamp. If the object is too close to the light, your eye struggles to separate it. It may be bright enough in principle. It may be reflecting plenty of light, but the glare around the lamp overwhelms it. Mercury has the same problem, except the lamp is the sun. The planet orbits inside Earth's orbit. It is closer to the sun than we are. So from Earth, Mercury always appears near the sun in the sky. It can only be seen before sunrise or after sunset, when the sun itself is below the horizon, but Mercury is still far enough from it in apparent angle to remain visible. That angle is called elongation. When Mercury is east of the sun, it appears in the evening sky after sunset. When it is west of the sun, it appears in the morning sky before sunrise. Greatest elongation means it is as far from the sun in our sky as that orbital arrangement allows. But even greatest elongation is not a guarantee. Mercury can appear only a little more than 20 degrees from the sun at its best, depending on where it is in its stretched orbit. 20 degrees sounds generous until you try to observe something low in twilight. The horizon is not clean. It is full of haze, rooftops, mountains, trees, pollution, and the last scattered light of the day. A planet that would be easy to see in a black sky becomes difficult in a bright one. This is why Mercury is famous among observers, not because it is faint, but because it is inconvenient. At times, Mercury can be brighter than many stars. The problem is not only brightness. The problem is location. The sky hides objects not by removing them, but by placing them where our senses are weakest. Mercury is a lesson in that kind of hiding. For most of human history, the planets were not worlds. They were wandering lights. The stars held their patterns. Night after night, season after season, constellations rose and set with a grand regularity. But a few lights disobeyed the background. They drifted. They paused. They reversed. They brightened and faded. They kept their own schedules. Mercury was the most restless of these. It moved quickly because it is close to the sun and travels around it in only 88 Earth days. But ancient skywatchers did not know that. They saw light that appeared in the morning, disappeared into the sun, returned in the evening, disappeared again, and never strayed far from daylight. In some cultures, its morning and evening appearances were treated as different objects until careful observation connected them. Venus has a similar pattern, but Venus announces itself. It blazes. It hangs in the sky long enough to become myth. Mercury is subtler. It demands timing. It demands a horizon. It demands attention at the edges of day, when the human mind is often turning away from the sky. That alone makes Mercury strange. It is one of the classical planets known since antiquity, yet it is also the one many modern people have never seen. We have sent spacecraft to the outer solar system. We have imaged Pluto. We have landed machines on Mars. We have flown through the rings of Saturn. But Mercury, the nearest planet to the Sun, remains observationally shy from the ground. It is not far in the grand scale. It is hidden by alignment. And alignment is one of the great themes of astronomy. The sky is full of apparent relationships that are not physical relationships. The Moon can pass in front of the Sun, not because they are similar objects, but because the Moon is small and close while the Sun is enormous and distant. Venus and Jupiter can appear near one another, not because they are neighbors, but because our line of sight places them together. Mercury can vanish in sunlight, not because it is absent, but because it lies too close to the direction of the most overwhelming object in our sky. Astronomy begins when we stop trusting appearances completely. The night sky is beautiful, but it is not honest in any simple way. It compresses depth into a dome. It turns distance into brightness. It makes unrelated objects seem close. It makes moving bodies look fixed until patient watching reveals otherwise. Mercury is one of the places where that illusion breaks open. During greatest eastern elongation, Mercury sits to the east of the Sun as seen from Earth. Since the sky appears to rotate westward as Earth spins, objects east of the Sun set after the Sun. That gives Mercury a small window of evening visibility. You look low toward the western sky after sunset, and if the planet is high enough above the horizon and the air is clear, it appears as a small steady point. It does not twinkle much, because planets present tiny disks rather than point sources like stars. But near the horizon, atmosphere can disturb everything. The light passes through more air. It reddens, it dims, it shimmers. Mercury is often seen through the thickest part of the atmosphere, near the place where the sky is least forgiving. There is something fitting about that. Mercury is difficult from the outside because Mercury is extreme on the inside. The planet orbits at an average distance of about 58 million kilometers from the Sun, but its orbit is not a neat circle. It is the most eccentric orbit of any major planet in the solar system. Eccentric here does not mean strange in personality, though Mercury has plenty of that. It means stretched. At perihelion, Mercury is much closer to the Sun. At aphelion, it is farther away. The difference matters. When Mercury is near perihelion, sunlight is far more intense. When it is farther out, the solar heat weakens, though it is still much stronger than anything Earth receives. From Mercury's surface, the Sun would look more than 3 times wider than it appears from Earth, and sunlight can be several times more intense. Imagine noon on a world with almost no atmosphere to soften the light. There is no blue sky. There are no clouds. There is no weather in the familiar sense. There is no breeze moving dust across the ground. The Sun rises into blackness. It pours light directly onto rock. Surface temperatures can climb high enough to melt lead. Then night comes. Because Mercury has almost no atmosphere to hold heat, the dark side cools brutally. Temperatures can plunge hundreds of degrees below freezing. The same planet can host scorching days and frozen nights, not because it is far from the Sun, but because it lacks the atmospheric blanket that makes temperature memory possible. On Earth, air and oceans redistribute heat. They soften extremes. A desert can be cold at night, but it is still protected by an atmosphere. Mercury has only a tenuous exosphere, a whisper of atoms knocked from its surface by sunlight, impacts, and the solar wind. It is not an atmosphere you could stand inside and feel. It is not a sky. It is a nearly empty boundary between rock and space. So Mercury is naked. It receives the Sun almost directly, and it loses heat almost directly. That makes it one of the most physically dramatic environments in the inner solar system. But the deeper strangeness is time. Mercury orbits the Sun every 88 Earth days. That is its year. Its rotation, however, is locked into a pattern called a 3-to-2 spin-orbit resonance. For every 2 orbits around the Sun, Mercury rotates 3 times relative to distant stars. This is not the same as being tidally locked like the Moon is to Earth. The Moon keeps one face toward Earth. Mercury does not keep one face permanently toward the Sun for a long time. Astronomers thought it might. The assumption made sense from a distance. Close objects can become locked by tides. But radar observations in the 20th century revealed the stranger truth. Mercury rotates 3 times for every 2 trips around the Sun. The result is a day that feels almost impossible by Earth standards. A solar day on Mercury, meaning sunrise to sunrise, lasts about 176 Earth days. That is 2 Mercury years. A year is shorter than a day. That sentence is easy to say and hard to imagine. On Earth, day and year are separate rhythms. The day is the spin. The year is the orbit. We feel them as different scales of time. Wake and sleep belong to the day, seasons belong to the year. But Mercury scrambles that intuition. The movement around the Sun and the turning of the planet are locked together in a resonance that produces a slow alien cycle of light. On some parts of Mercury, the Sun would behave in a way that seems broken. Because Mercury moves fastest when it is closest to the Sun, its orbital motion can temporarily overtake the apparent motion created by its rotation. A person standing in the right place would see the Sun rise, slow down, stop, reverse direction for a while, then move forward again. Near other longitudes, the Sun can appear to rise, set, and rise again in a strange double motion. This is not fantasy. It is orbital mechanics made visible. The sky over Mercury would teach you that the apparent motion of the Sun is not simply about a planet turning. It is about rotation and revolution combined. It is about the geometry of a moving world around a massive star. On Earth, we are spared most of this complexity. The Sun rises in the east and sets in the west because Earth rotates quickly compared with its orbit. The variations exist, but they are gentle. On Mercury, they become theatrical. The smallest planet turns time into something unfamiliar. And then there is its body. Mercury is only slightly larger than Earth's moon, but it is much denser. Beneath its gray, cratered surface is a huge iron-rich core that takes up a remarkable fraction of the planet. In broad terms, Mercury looks like a planet that has too much metal for its size. Why? That question has haunted planetary science for decades. One possibility is that Mercury formed from material unusually rich in metal near the young Sun. Another is that the early planet suffered a giant impact that stripped away much of its rocky mantle, leaving behind a dense core. Another is that the heat and conditions of the inner solar nebula altered the composition of what could condense there. The truth may involve more than one process, but the result is clear. Mercury is a metal-heavy world. Its core is not merely a buried detail. It affects the planet's gravity, its contraction, and its magnetic field. Mercury has a global magnetic field weak compared with Earth's but real. That surprised scientists. A small planet should have cooled quickly. If its core were completely solid, the dynamo processes that generate a magnetic field might have died long ago. Yet Mercury still has magnetism. That means something inside it is not as dead as its surface looks. The surface is ancient and battered. It resembles the Moon at first glance, with craters everywhere. But Mercury is not the Moon. It has volcanic plains. It has enormous cliffs called lobate scarps, formed as the planet cooled and contracted. Imagine a metal-rich world slowly shrinking over billions of years, its crust wrinkling as the interior loses heat. The result is geology written as compression. Mercury looks still, but stillness can be a record of violence. Its largest impact basin, Calories, is roughly 1,500 kilometers across. The impact that formed it was so powerful that it sent shockwaves through the planet, disturbing terrain on the opposite side. A crater is not just a hole. On planetary scales, it is a statement about energy. It tells you that something arrived at cosmic speed, that rock behaved briefly like fluid, that a world rang. Mercury has been ringing for billions of years in frozen form. When spacecraft finally saw it closely, they found not a simple dead rock, but a planet with layers of history. The first spacecraft to visit Mercury was Mariner 10 in the 1970s. It flew past the planet 3 times, using a gravity assist from Venus to reach the inner solar system. It imaged part of the surface and discovered Mercury's magnetic field. But it did not map the whole planet. For decades, large portions of Mercury remained unseen in detail. That fact is astonishing. The nearest planet to the Sun, one of Earth's inner neighbors, was only partly known well into the space age. The difficulty is not distance alone. Getting to Mercury is hard. That may sound wrong. Mercury is closer to the Sun. Shouldn't falling inward be easy? But orbital mechanics does not reward intuition. Earth is already moving around the Sun at about 30 kilometers per second. A spacecraft launched from Earth carries that sideways motion. To reach Mercury and stay there, it must lose a large amount of orbital energy. It must fall inward, but also slow down enough not to simply whip past the planet or plunge into the Sun. The Sun's gravity dominates everything. The closer a spacecraft travels, the faster it tends to move. Reaching Mercury is like trying to step onto a fast-moving platform while sliding downhill. You need careful braking. But rockets carry limited fuel. So missions use gravity assists, passing planets in carefully designed trajectories that trade energy and momentum. Mariner 10 used Venus. Messenger used Earth, Venus, and Mercury itself. Bepi Colombo has used a long chain of flybys as well. The route to Mercury is not a straight line, it is a negotiation. NASA's Messenger mission launched in 2004 and entered orbit around Mercury in 2011. It became the first spacecraft ever to orbit the planet. It studied Mercury's surface, space environment, geochemistry, and gravity. It mapped the entire planet. It transformed Mercury from a partial sketch into a world. Messenger found evidence supporting water ice in permanently shadowed polar craters. That sounds absurd at first. Water ice on the planet closest to the Sun, but Mercury's poles contain craters whose floors never receive direct sunlight. Because the planet's axial tilt is extremely small, sunlight at the poles skims the horizon. Deep crater interiors can remain in permanent shadow, cold enough to preserve volatile materials for long periods. Radar observations from Earth had already hinted at bright deposits. Messenger helped confirm that these regions matched permanently shadowed areas and supported the presence of ice, often buried beneath darker material. So Mercury is not simply fire, it is fire beside darkness. A planet where the equator can bake and polar shadows can preserve ice. This is the kind of contradiction that makes planetary science humbling. We carry simple labels for worlds. Mercury is hot, Venus is cloudy, Mars is red, Jupiter is giant, Saturn has rings. But the real worlds resist being reduced. Mercury is the closest planet to the Sun, yet it shelters cold traps. Venus is hotter than Mercury, not because it is closer, but because its atmosphere is a greenhouse furnace. Mars looks desert dry, yet its history is shaped by water. The labels help us begin, then fail us. Mercury fails the label almost immediately. It is not just hot, it is not just small, it is not just fast. It is a world where the geometry of sunlight creates both extremes, where metal dominates the interior, where magnetism survives against expectation, and where its orbit once pointed toward a missing piece in our theory of gravity. That missing piece is one of the most important stories in science. To understand it, picture an ellipse. Planets do not orbit the Sun in perfect circles. Johannes Kepler recognized this in the early 17th century by studying the motion of Mars. A planet follows an ellipse with the Sun at one focus. In Newton's theory, an isolated planet orbiting a perfectly spherical Sun would trace the same ellipse again and again. But the real solar system is not isolated. Other planets tug on one another. The ellipse itself slowly rotates. The closest point to the Sun, called perihelion, advances over time. For Mercury, this precession is especially noticeable because it orbits close to the Sun, moves quickly, and follows a relatively eccentric path. Most of Mercury's perihelion precession can be explained by Newtonian gravity and the gravitational pulls of other planets. But in the 19th century, astronomers found a small leftover. Tiny but persistent. About 43 arcseconds per century could not be accounted for. An arcsecond is a very small angle. There are 60 arcseconds in an arcminute, 60 arcminutes in a degree. 43 arcseconds per century is not something a casual observer would ever notice. It is the kind of discrepancy that lives inside careful tables and patient calculations. But science often changes because of small leftovers. The planet Uranus had once deviated from predictions, and that deviation led to the discovery of Neptune. So when Mercury's orbit showed an unexplained shift, some astronomers suspected another unseen planet inside Mercury's orbit. It was called Vulcan. People searched for it. Reports appeared. Shadows near the Sun were interpreted. Eclipses became opportunities. But Vulcan was never found because Vulcan was not there. The missing planet was not a planet. It was a sign that gravity itself had been described incompletely. In 1915, Albert Einstein used general relativity to explain Mercury's anomalous perihelion precession. Gravity, in his new theory, was not simply a force acting across space. Massive objects shaped spacetime, and planets moved along paths determined by that curvature. Near the Sun, where gravity is stronger and velocities are higher, the difference from Newton's predictions becomes measurable. Mercury was the perfect witness. It lived close enough to the Sun for spacetime curvature to show its hand. When Einstein's calculation matched the unexplained 43 arcseconds per century, it was more than a mathematical victory. It was a signal that the universe was deeper than the old picture. Newton's laws were not wrong in ordinary conditions. They remain astonishingly accurate for most everyday and even astronomical purposes. But they were not final. Mercury revealed the seam. The smallest planet helped break the largest theory of its age. There is something quietly unsettling about that. We imagine revolutions arriving through dramatic discoveries. A new planet, a strange star, a great explosion in the sky. But sometimes the revolution is a tiny mismatch in the motion of a small world that few people ever see. Mercury did not shout. It drifted slightly differently than expected. And that was enough. This is why the June 2026 elongation is more than a skywatching note. It is a doorway. A person standing under the evening sky might see Mercury for a few minutes, low in the west, and think they are seeing a small bright point. But that point carries the history of ancient astronomy, the geometry of inner planets, the violence of planetary formation, the endurance of ice in darkness, the difficulty of spacecraft navigation, and the first observational triumph of general relativity. A dot can contain a universe of meaning. The reason Mercury appears low in twilight comes from the architecture of the inner solar system. Earth orbits third from the Sun. Venus and Mercury orbit inside us. Mars, Jupiter, Saturn, Uranus, and Neptune orbit outside us. Outer planets can appear opposite the Sun in our sky. When Jupiter is at opposition, it rises around sunset and stays visible all night. That is because Earth sits between Jupiter and the Sun. The geometry places Jupiter in the dark sky. Mercury can never do that. It can never be opposite the Sun from Earth's point of view, because its orbit is always inside ours. It is always seen near the Sun's direction, either just ahead of it in the morning or just behind it in the evening. Its visibility is restricted by geometry before weather or brightness even enter the problem. This is also why Mercury shows phases. Like the Moon and Venus, Mercury presents different portions of its sunlit side to Earth. Through a telescope, it can appear as a small crescent, a half disk, or a gibbous disk. Galileo's observations of Venusian phases helped undermine the old Earth-centered picture. Mercury's phases fit the same deeper truth. These worlds orbit the Sun, but Mercury is difficult to study from the ground because it is small, close to the Sun in the sky, and often observed through turbulent low atmosphere. Even powerful telescopes face limits. The Hubble Space Telescope cannot safely point too close to the Sun, which means Mercury is not a simple target even for our great orbital observatory. To know Mercury, we had to go there, but going there forced us to learn humility about motion. A spacecraft headed inward gains speed as it falls toward the Sun. To be captured by Mercury, it must shed energy. Messenger took a long route across the inner solar system, using flybys to gradually adjust its path. It flew past Earth once, Venus twice, and Mercury 3 times before finally entering orbit. The journey took almost 7 years. The planet closest to the Sun was not reached by a simple plunge. It was reached by patience. This patience matters because Mercury sits in an environment that is rough on machines. The spacecraft must endure intense sunlight and heat. It must manage thermal extremes. It must operate near a massive star while orbiting a small planet with weak gravity. Navigation has to be precise, and instruments must be protected from conditions more severe than those around Earth or Mars. Bepi Colombo, the joint European and Japanese mission, continues this long effort. Launched in 2018, it uses solar electric propulsion and multiple gravity assists, including flybys of Earth, Venus, and Mercury. Its arrival in Mercury orbit is planned for late 2026. The mission includes 2 science orbiters. one focused on the planet itself, and one focused on Mercury's magnetosphere. That matters because Mercury has a magnetic field and interacts directly with the solar wind. Earth's magnetic field creates a large protective bubble, a magnetosphere that deflects charged particles from the Sun. Mercury's magnetosphere is much smaller and weaker, but because the planet is so close to the Sun, it lives in a harsher solar environment. The solar wind can compress and disturb its magnetic bubble. Particles can reach the surface. At Mercury, the relationship between rock, magnetic field, and solar particles is intimate. It is almost as if the planet has no privacy from the Sun. The Sun not only lights Mercury, it sculpts its space environment. It knocks atoms from the surface. It drives variations in the exosphere. It pushes against the magnetic field. It dominates Mercury's sky, its temperature, and its orbital history. Mercury is a world under pressure. But pressure is not the same as simplicity. Consider the polar ice again. The existence of ice on Mercury does not contradict the planet's closeness to the Sun. It reveals how geometry and topography can create hidden environments. A crater floor in permanent shadow is not experiencing Mercury as a whole. It is experiencing its local horizon. If sunlight never reaches it, and if heat is not carried efficiently by air, the cold can remain. On Earth, atmosphere connects places. Wind carries heat. Water moves energy. Weather ties regions together. On Mercury, isolation is easier. A sunlit slope and a shadowed crater floor can belong to different thermal worlds, separated by only a small distance. This is one of the reasons airless bodies are so strange. They do not average themselves in the way Earth does. They preserve extremes side by side. The Moon has similar cold traps at its poles, which is why lunar ice is so important for future exploration. Mercury's polar deposits show that even near the Sun, darkness can be deep enough to protect ancient material. The solar system is full of these hidden pockets where our simple maps of hot and cold fail. Mercury teaches that environment is local. A planet can be defined by the Sun and still contain darkness the Sun never touches. There is a poetic temptation here, but the science is already strange enough. A tiny planet close to the Sun has ice in shadowed craters, a magnetic field from a core that should have cooled more than it did, a day longer than its year, and an orbit that helped reveal curved spacetime. If Mercury were fictional, it might seem over-designed, yet it is real, and for a few evenings in June 2026 it can be looked for in the twilight. Finding it requires a different kind of attention from looking at the Moon or Jupiter. You cannot simply step outside at midnight. You need timing. You need to know where the Sun has set. You need a clear western horizon. You need to wait until the sky darkens enough, but not so long that Mercury has already followed the Sun downward. That narrow window is part of the experience. Some astronomical objects are generous. The Moon makes itself obvious. Orion rises in winter and announces its shape. Jupiter can shine like a steady lantern for months. Mercury feels like a test of awareness. It asks whether you can notice a planet at the boundary between day and night. In that sense, Mercury is not just an object. It is a lesson in thresholds. It appears at dawn or dusk when the sky is neither one thing nor the other. It orbits between Earth and the Sun, in the inner region we cannot easily stare into. It sits between ancient naked-eye astronomy and modern spacecraft science. It sits between Newton and Einstein, between fire and ice, between visibility and disappearance. Mercury is a boundary world. That may be why it has always attracted a certain kind of mythic meaning. The Roman god Mercury was a messenger, swift-footed, moving between realms. The planet's speed made the name appropriate. It zips around the Sun faster than any other planet. But the messenger symbolism feels deeper now. Mercury carried messages to us from places we did not know we needed to examine. Its motion carried a message about gravity. Its density carries a message about planetary formation. Its ice carries a message about hidden cold in the inner solar system. Its visibility carries a message about the difference between what exists and what is easy to see. In science, difficulty often points toward value. Not always. Some things are hard because they are trivial and inconvenient, but often the hard-to-see object reveals the limits of our assumptions. Mercury is hard to see because it is close to the Sun in our sky. It is hard to reach because falling inward requires losing energy. It is hard to understand because its history is encoded in a dense metal-rich body that does not match simple expectations. Each difficulty forced a better method. Ancient observers needed patience. Telescopic observers needed timing and caution. Spacecraft engineers needed gravity assists and thermal protection. Theorists needed a new understanding of spacetime. Mercury did not make things easy. That is part of why it mattered. Let's stay with the orbit a little longer because Mercury's orbit is the engine behind many of its mysteries. A circular orbit is easy to imagine. A planet moves at a steady distance around a star. But Mercury's path is more stretched. At closest approach, it receives much more solar energy than it does at its farthest point. It also moves faster near perihelion, in accordance with Kepler's second law, which says that a line from the Sun to a planet sweeps out equal areas in equal times. In plain language, planets speed up when they are closer to the Sun and slow down when they are farther away. On Earth, this effect exists but is modest. On Mercury, it is dramatic. The combination of eccentric orbit and spin-orbit resonance creates the strange solar motions we mentioned earlier. The Sun's apparent path in Mercury's sky can pause and reverse. This does not mean the planet physically changes rotation direction. It means the apparent motion of the Sun as seen from the surface depends on both spin and orbital speed. Near perihelion, Mercury's rapid orbital motion changes the balance. This is a reminder that sky motions are composite illusions. When you see the Sun move across Earth's sky, you are not seeing the Sun move around Earth. You are seeing Earth rotate. When you see Mars reverse direction against the stars, you are not seeing Mars turn around in space. You are seeing Earth pass it in orbit. When you see Mercury near the horizon after sunset, you are not seeing a planet located near the Sun in physical distance at that moment in any simple way. You are seeing a line-of-sight relationship from a moving platform. The sky is a projection of motion onto perception. That is why ancient astronomy was so difficult and so brilliant. Without spacecraft, without modern computers, without photography, skywatchers had to separate appearance from structure. They watched cycles repeat. They recorded positions. They learned that the wandering lights obeyed patterns, even when those patterns seemed confusing. Mercury's pattern was one of the hardest because it stays near the Sun. To build a model of the solar system, humanity had to understand that the apparent dome of the sky was not the architecture of reality. The Earth was moving. The planets were orbiting the Sun. Their brightness and positions changed because of geometry. The sky was not a ceiling with lights attached. It was depth collapsed into vision. Mercury helped force that realization because it never behaved like a fixed star. It wandered close to the Sun and returned. In the Copernican picture, that behavior makes sense. Mercury is inside Earth's orbit. It appears on one side of the Sun, passes between Earth and Sun at inferior conjunction, appears on the other side, then passes behind the Sun at superior conjunction. Its morning and evening appearances are not separate objects. They are the same world moving around the star. A modern planetarium app can show this instantly. But instant clarity can hide the achievement. It took generations to decode what now appears obvious on a screen. And Mercury still resists us in practice. Knowing where it is does not mean you can always see it. The app may point to a place above the horizon. But clouds, haze, glare, and buildings can erase the planet from your experience. There is a gap between knowledge and observation. Astronomy lives in that gap. You can know that Mercury is there, and still fail to see it. That failure is not meaningless. It teaches scale. It teaches atmosphere. It teaches that the universe is not arranged for our convenience. Mercury's physical world carries the same lesson. It is tempting to imagine the planet as a smaller moon, gray and cratered. But MESSENGER revealed chemical differences and geological features that complicate that comparison. Mercury's surface contains volcanic plains, unusual hollows, and evidence of volatile elements that challenge simple high-temperature formation stories. The planet closest to the Sun is not completely depleted of substances that should evaporate easily. That fact forced scientists to rethink how Mercury formed and evolved. The hollows are especially intriguing. They are shallow, irregular depressions with bright interiors and halos, found in many places on Mercury. They appear geologically young compared with surrounding terrain, and they may form when volatile materials are lost from the surface or near surface. They are not impact craters in the ordinary sense. They look like the ground has been eaten away. A planet thought to be dry and inert shows signs of ongoing or relatively recent surface modification. Again, Mercury refuses simplicity. Its surface also records contraction. As the interior cooled, the planet shrank slightly. The crust had to adjust, producing long cliffs where one block of crust was pushed over another. These scarps can run for hundreds of kilometers. They tell us that a planet can change shape as it loses heat, that geology does not require plate tectonics like Earth's to create large structures. Earth's geology is dynamic because of internal heat, water, atmosphere, and plate motion. Mercury's geology is quieter, but not blank. It is the geology of impacts, volcanism, cooling, contraction, and solar exposure. It is a world written in scars rather than weather. And because there is little atmosphere, those scars last. On Earth, erosion is relentless. Rain softens mountains. Wind moves dust. Rivers cut valleys. Life alters rock. Plate tectonics recycles crust. Earth forgets much of its earliest surface. Mercury remembers. So does the Moon. So do many airless bodies. Their surfaces are archives of bombardment and ancient processes. But Mercury's archive lies close to the Sun, exposed to a stronger solar wind and more intense thermal cycling. Its memory has been written under harsher light. That makes it valuable for understanding the early solar system. The inner planets did not form in isolation. Mercury, Venus, Earth, and Mars are related outcomes of the same protoplanetary disk. But they diverged dramatically. Mercury became small and metal-rich. Venus became a runaway greenhouse world. Earth became ocean-bearing and alive. Mars became cold, thin-aired, and partially frozen. The differences between them are not trivia. They are clues to the conditions that make planets what they are. Mercury is one endpoint. By understanding it, we better understand why Earth is not like it. That may be the quiet value of every planetary mission. A spacecraft does not merely study another world. It studies the range of possibilities that Earth escaped. Mercury shows us a version of a rocky planet stripped down to essentials: stone, metal, sunlight, impact history, weak magnetism, and time. No oceans, no thick air, no biosphere, no blue sky, just a planet close enough to the Sun that daylight becomes a physical hazard, yet distant enough from simplicity to surprise us. The more we learn about Mercury, the less it feels like a small preliminary planet. It feels like a compressed puzzle. The upcoming and ongoing work of Bepi Colombo matters because Messenger answered many questions but raised others. Bepi Colombo will bring 2 orbiters with complementary instruments. The European orbiter will study Mercury's surface and interior. The Japanese orbiter, called MIO, will focus on the magnetosphere and space environment. Together they can examine the planet as both a body and a system embedded in the Sun's influence. This dual view is important. A planet is not only its surface, it is also its interior, its gravity, its magnetic field, its exosphere, and its relationship with the star it orbits. Mercury cannot be understood as a rock alone. It must be understood as a rock inside a magnetic and radiation environment, moving along an eccentric path close to the Sun. In that sense, Mercury is one of the best laboratories for studying star-planet interaction. Exoplanet scientists care about this too. Many planets found around other stars orbit extremely close to their stars. Some are rocky worlds blasted by intense radiation. Some are tidally locked. Some may have lost atmospheres. We cannot visit them. We often know them only by shadows in starlight or tiny gravitational wobbles. Mercury, in our own solar system, is not the same as those worlds, but it gives us a nearby example of what happens when a rocky planet lives under strong stellar influence. The innermost planet becomes a reference point for worlds we may never see directly. That is another reason the small planet matters. It helps us read distant systems. But for the human observer, Mercury begins with the naked eye. There is something powerful about that contrast. The same object that requires advanced spacecraft and general relativity can also appear as a small point in twilight. You do not need a telescope to see it during a favorable elongation. You need knowledge, timing, and a clear horizon. That is a rare kind of accessibility. Not easy accessibility, earned accessibility. A person who sees Mercury knows they have caught something temporary. The planet will not stay where it is. Night after night it will shift. Its angle from the Sun will change. It will sink back toward glare. Eventually it will pass between Earth and the Sun, lost again. Later it will reappear in the morning sky on the other side of the Sun from our perspective. This cycle repeats. Mercury is always returning and disappearing. The rhythm is fast compared with other planets. Its synodic period, the time it takes to return to the same general configuration relative to Earth and the Sun, is about 116 days. That means there are multiple elongations each year, some better than others depending on the season, hemisphere, orbital position, and angle of the ecliptic to the horizon. The ecliptic is the apparent path of the Sun across the sky, which is really the plane of Earth's orbit projected onto the celestial sphere. The planets stay near it because the solar system is relatively flat. When the ecliptic meets the horizon at a steep angle after sunset, Mercury can stand higher in the sky and become easier to see. When it meets at a shallow angle, Mercury may be far from the Sun in angular terms but still low and difficult. So greatest elongation is not the whole story. Geometry has layers. The planet's distance from the Sun on the sky matters. The tilt of the ecliptic matters. The observer's latitude matters. The local horizon matters. Atmospheric clarity matters. Timing matters. This is why sky events can be both universal and local. The date may be listed globally, but the experience depends on where you stand. On June 15, 2026, Mercury's greatest eastern elongation gives observers an evening opportunity, but every observer will have their own sky. Some will have monsoon clouds, some will have city haze, some will have hills blocking the west, some will have a clean horizon over water and see Mercury clearly. Astronomy is cosmic, but observation is personal. The universe arrives through weather. That is easy to forget when we talk in dates and diagrams. A diagram of elongation is clean. Sun at the center, Earth on one orbit, Mercury on another. Lines drawn between them, angles labeled. The explanation fits on a page. Then the actual evening comes, and the sky is orange, humid, uneven, alive with dust and cloud. You stand outside waiting for a tiny point to appear. The diagram becomes an experience. The geometry becomes patience. This is one of the reasons naked eye astronomy still matters. It reconnects theory with the body. You feel the horizon. You feel the fading light. You understand why ancient observers needed discipline. You realize that seeing a planet is not always automatic. It is an event created by the object, the Earth, the atmosphere, and your own attention. Mercury rewards that attention with very little spectacle. It will not show rings. It will not show cloud bands. It will not reveal craters to the naked eye. It is a point, but that point is honest in a deeper way. It tells you that knowledge can transform perception. Without context, Mercury is a faint dot near sunset. With context, it is a metal-rich planet racing around the Sun, a world where a day lasts 2 years, a place visited by spacecraft after elaborate gravitational choreography, a witness to the curvature of spacetime. The dot does not change, you do. This is true across astronomy. A star becomes a sun when you understand it. A fuzzy patch becomes a galaxy. A moving point becomes an asteroid. A brief streak becomes a grain of cosmic dust burning in the atmosphere. The sky is not only seen, it is interpreted. Mercury demands interpretation because it gives the eye so little, and perhaps that is why it belongs so well to a long, quiet story. It is not loud, it is not obvious, but it sits at the root of enormous ideas. Think again about Newton. Newtonian gravity unified the fall of an apple and the orbit of the moon. It gave the solar system mathematical structure. It allowed astronomers to predict motions with extraordinary precision. It remains one of the great achievements of human thought. To say Mercury exposed a flaw in Newtonian gravity is not to diminish Newton. It is to show how powerful a theory must be before a tiny discrepancy matters. A weak theory fails everywhere. A strong theory fails only at the edges. Mercury was one of those edges. The unexplained precession was not a collapse of celestial mechanics. It was a small excess left after known effects were accounted for. That is exactly why it was profound. The old theory worked so well that the leftover could not be dismissed as chaos. It had to mean something. Einstein's general relativity did not merely patch Mercury's orbit. It reimagined the stage on which orbits happen. Space and time were not passive containers. They formed a dynamic geometry, affected by mass and energy, Planets were not pulled through absolute space by a mysterious action at a distance in quite the old way. They followed paths through curved spacetime. Mercury, closest to the Sun among the planets, traced that curvature in its slow-turning orbit. Every time Mercury reaches perihelion, the closest point of its orbit is slightly shifted compared with where it would be in a purely Newtonian calculation. The effect is tiny, but over time it accumulates. This is the universe whispering that geometry is physical. The whisper was heard. There is a broader lesson here about anomalies. An anomaly is not automatically a revolution. Most anomalies vanish with better data, better models, or less excitement. Science is full of false alarms. But some anomalies survive. They sit quietly at the edge of explanation. They become invitations. Mercury's perihelion was one of those invitations. It invited the possibility of Vulcan, and Vulcan failed. It invited refinements in solar shape, and those were not enough. It invited a deeper theory, and general relativity answered. The answer did not come from Mercury alone. Einstein's theory had many roots, mathematical and conceptual, but Mercury became one of its early tests. Later came the bending of starlight near the Sun, gravitational redshift, time dilation, gravitational waves, black hole imaging, and the precision technologies of the modern world. But Mercury was there near the beginning, a small planet with a stubborn orbit. This is why looking at Mercury can feel different once you know the story. You are not only seeing a planet, you are seeing evidence that the old universe gave way to a stranger one. A world low in twilight helped reveal that space and time are not rigid. That should unsettle us a little, because the change from Newton to Einstein was not merely a correction. It was a warning. Our best descriptions can be accurate and incomplete at the same time. They can work beautifully until we look in the right place with enough precision. Mercury was the right place, close to the Sun, fast, eccentric, observable over long periods. Small in the sky, but loud in the equations. The planet that hides in glare became the planet that exposed hidden curvature. There is symmetry in that. The observational Mercury hides because of sunlight. The theoretical Mercury revealed what was hidden inside gravity. The more we follow this planet, the more it becomes a study in concealment and revelation. Its surface hides ice in shadows. Its orbit hides relativity in a tiny precession. Its position hides it in twilight. Its small size hides a huge core. Its dead-looking face hides a history of volcanism, contraction, and magnetic survival. Mercury is a planet of hidden facts. That makes the working title almost literal. The planet hides in the Sun's glare, but not only visually. It hides behind assumptions. One assumption is that the closest planet to the Sun must be the hottest. But Venus is hotter because of its atmosphere. Another is that a small planet must be geologically boring. Mercury's scarps, hollows, volcanic plains, and magnetic field say otherwise. Another is that proximity means accessibility. Mercury is near in orbital order but difficult to reach. Another is that naked eye visibility means familiarity. Mercury has been known for thousands of years, yet remained poorly mapped until recently. Familiarity can be shallow. We can name a thing long before we understand it. That is one of the strange truths of the solar system. The planets were named before they were worlds. They entered language as lights, gods, omens, calendar markers. Only later did telescopes, physics, and spacecraft turn them into places. Mercury carried a name for millennia before humans saw its global surface. A name is not knowledge, it is a beginning. Mercury's modern exploration also reminds us that the solar system is not equally studied. Mars receives enormous attention because it is accessible, visible, potentially habitable in the past, and culturally magnetic. The Moon is close. Venus is difficult but brilliant and nearby. Jupiter and Saturn are spectacular. Mercury has often been overshadowed. But neglect is not the same as insignificance. The least explored places can be the ones that change the frame. Bepi Colombo's arrival will matter not because Mercury is unknown in every way, but because it is known enough for better questions. What is the exact state of its core? How did its magnetic field evolve? What is the composition of its surface? How do volatiles survive and move? How does its magnetosphere respond to the solar wind? What does its formation tell us about the earliest inner solar system? Good science does not end mystery. It refines it. Messenger gave Mercury a new reality. Bepi Colombo will sharpen it, but the planet will remain difficult from Earth. Even after spacecraft map its surface in exquisite detail, a person looking for Mercury will still have to search low in twilight. The ancient challenge remains. Technology can transform knowledge without changing the basic human experience of seeing the planet. That continuity is beautiful. A skywatcher today and a skywatcher 2,000 years ago can both stand after sunset and hunt for the same elusive light. The modern observer may know about perihelion precession, magnetic fields, and polar ice. The ancient observer may have known only pattern and brightness, but both share the act of attention. The planet has not become easier just because we understand it better. There is humility in that too. When you look at Mercury, you are looking at a world that has shaped human thought from the naked eye era to relativity to spacecraft exploration. It links the oldest astronomy with the newest. It is visible without instruments, yet fully understandable only through mathematics, physics, engineering, and patient data. That is the kind of object the solar system gives us again and again. Simple enough to see, deep enough to never finish. Now consider what Mercury would be like as a place. Imagine standing there in a pressurized suit. Though no human is anywhere near doing this, the ground under your boots is gray-brown, dusty, and broken. The horizon is close because the planet is small. The sky is black even in daytime. The sun is enormous, too bright to look at, a white disk with dangerous power. There is no sound carried by air, no wind, no birds, no clouds, no blue. Your shadow is hard-edged. If you are near the equator in sunlight, heat is a serious threat. If you are in darkness, cold is. The environment does not forgive poor timing. The slow solar day means sunrise and sunset are long processes, and at some longitudes the sun's strange apparent motion would make time itself feel unreliable. A clock would still tick normally, your body would still measure seconds, but the sky would refuse Earth habits. This is one of the values of imagining other worlds carefully. It separates what is truly universal from what is merely local. We think of sunrise as daily because Earth makes it daily. We think of the sun's path as simple because Earth's rotation and orbit make it feel simple. We think of weather as a planetary fact because Earth has air and water. Mercury strips away those assumptions. On Mercury, a day is not a day as we know it. Weather is not weather. A hot planet can have ice. A small planet can have a magnetic field. A faint dot can carry a revolution in physics. The solar system is not a set of larger and smaller Earths. It is a set of experiments run under different initial conditions. Mercury is one of the harshest experiments, and its harshness began early. The formation of Mercury remains debated. The giant impact hypothesis is attractive because it could remove outer rocky layers and leave a metal-rich body, but it has complications. The chemistry of Mercury includes volatile elements that might not survive a simple high-energy stripping event as easily as expected. Other models suggest that Mercury formed from metal-rich material or that processes in the early disk sorted material by composition. Scientists continue to test these ideas using data from surface composition, gravity, and interior structure. The point is not that we have no answers. The point is that the answers are not simple. A planet is not a single event. It is a history of formation, bombardment, differentiation, cooling, volcanism, solar exposure, and orbital evolution. Mercury's present state is the compressed result of billions of years. When you see it in the evening sky, you see none of that directly. You see a dot. But astronomy is the art of reading dots. The ancients read Mercury's cycles. Newtonian astronomers read its orbit. Einstein read its anomaly. Spacecraft read its gravity, surface, exosphere, and magnetic field. Bepi Colombo will read it again with better instruments and different angles. Each reading changes the meaning of the dot. That is why a sky event like greatest elongation matters for more than casual viewing. It offers a moment when public attention can attach to a planet normally ignored. A listing on an astronomy calendar says Mercury will be easier to see, but behind that listing is a story about why seeing it is hard, why the planet matters, and why the solar system is stranger than our simplified diagrams. A diagram shows Mercury as the first small circle around the Sun. Reality gives us a world whose orbit forced a new theory of gravity. There is a gap between diagram and reality. Dark matter radio lives in that gap. We take the simple line on the calendar and follow it inward until it becomes unsettling. The unsettling part is not danger. Mercury is not threatening Earth. Its elongation is not an omen. It will not affect us physically. The unsettling part is conceptual. It reminds us that visibility is not the same as significance. The most important clue can be small, low, brief, and easy to miss. Modern life often teaches us the opposite. Bright things get attention. Loud things feel important. The sky pushes back. Mercury says the quiet object near the glare may be carrying the deeper story. There is also something moving about Mercury's connection to twilight. Twilight is when categories soften. Day is ending, but night has not fully begun. The sky is bright enough to hide stars, dark enough to reveal planets. Human activity shifts. Birds change their calls. Street lights come on. The ordinary world becomes slightly unreal. Mercury appears there. Not in full darkness, not in full daylight, but in transition. It is the right setting for a boundary planet. If you try to see it, do not expect drama. Expect a search. Find a clear western horizon after sunset. Let the sky darken. Use Venus or Jupiter if they are nearby as brighter anchors. But remember that Mercury will be lower and closer to the sun's afterglow. Binoculars can help, but only after the sun is safely below the horizon. Never sweep near the sun with optics. The danger is real. Wait until sunset has passed, and if you do see it, notice how modest it looks. That modesty is part of the lesson. A world does not need to look impressive to be profound. Mercury's story also shows how astronomy connects different scales of human effort. There is the individual observer, alone under a fading sky. There are professional observatories measuring positions across centuries. There are mathematicians comparing prediction to reality. There are engineers designing spacecraft trajectories through the inner solar system. There are mission teams waiting years for orbit insertion. There are planetary scientists interpreting spectral lines, gravity fields, and crater shadows. All of them are, in different ways, looking at the same planet. Science is not one act, it is a chain of attention. Mercury has held that chain for a very long time. The ancient observer noticed its wandering. The early modern astronomer placed it in orbit around the sun. The 19th century calculator saw its stubborn precession. Einstein used it as evidence of spacetime curvature. Mariner 10 revealed a magnetic field. Messenger mapped its surface and supported polar ice evidence. Bepi Colombo now approaches with new instruments. A small planet has kept demanding better questions. That is perhaps the deepest reason to care. Not because Mercury is beautiful in the obvious way, not because it may host life, not because it is a likely destination for human settlement, but because it has repeatedly forced human understanding to become more precise. Precision is not cold. Precision is how awe survives contact with reality. A vague Mercury is a tiny hot planet. A precise Mercury is far stranger. Smallest planet, fastest orbit, highest orbital eccentricity among the major planets, huge iron core, weak magnetic field, exosphere, scarps from contraction, hollows, polar ice, 3-2 spin orbit resonance, anomalous perihelion precession explained by general relativity, difficult spacecraft target, twilight apparition. The more precise we become, the less boring the universe gets. That is the opposite of what many people fear about science. They worry explanation removes mystery. Mercury shows the reverse. The explanation multiplies mystery by giving it structure. A planet hiding in glare becomes a whole architecture of questions. As June 15th approaches, astronomy guides will tell people when and where to look. They will use clean phrases: greatest eastern elongation, evening visibility, low in the west after sunset. These phrases are useful, but behind them is a more intimate sentence. A planet that is almost always swallowed by the sun's light is briefly stepping far enough aside for us to notice it. Not far physically, far enough in angle, far enough for human eyes. That distinction is everything. The universe does not present itself as it is. It presents itself through angles, light, timing, instruments, and minds. Mercury's elongation is a reminder that astronomy is partly the science of where things are, and partly the science of how they appear from here. From here, Mercury hides. From Mercury, Earth would be another bright object in the sky, sometimes visible, sometimes near the sun, part of a different geometry. Every planet has its own astronomy. Every world has its own version of what is easy and what is hidden. That thought can rearrange the imagination. There is no universal sky. There are only skies from somewhere. Earth's sky is ours, and Mercury is difficult in it. But difficulty is not absence. The planet is there whether we see it or not, moving quickly through its orbit, turning slowly through its long day, carrying its old scars and its hidden ice, curving through spacetime near the sun. The evening sky does not tell us all of that. It only gives us a point of light. The rest we had to earn. And maybe that is the real story of Mercury. It is the planet that teaches us how much can be hidden behind a point, how much can be missed at the edge of glare, how a small mismatch can break open a theory, how a world can be close and still elusive. When the sun sets on June 15, 2026, Mercury will not become large. It will not become obvious. It will not perform for us. It will simply be better placed than usual. That is enough. The smallest planet does not need to shout. It has already changed the way we understand gravity. It has already forced spacecraft to dance through the inner solar system. It has already shown us ice where we expected only heat, and magnetism where we expected silence. It has already proven that the universe can hide its most important clues in the places we almost never look. So if you find yourself outside after sunset, watching the western horizon fade from gold to blue to black, remember that the first planet may be there, low and quiet, close to the sun's afterimage. You may see it for only a few minutes. You may miss it entirely. Either way, it is moving. Either way, it is carrying its message. Mercury is the messenger that keeps disappearing before we finish listening, and maybe that is why it remains so compelling. It does not offer itself easily. It asks us to calculate, to wait, to look carefully, to question what the sky seems to show us. It asks us to accept that the universe is not always hidden in darkness. Sometimes it is hidden in light. There is another reason Mercury feels like an edge case. It lives close to the region where human observation becomes dangerous. Looking near the sun is not like looking near the moon. The sun is not merely bright. It is physically hazardous to the eye through optical instruments. A telescope or binocular pointed too close to the sun can concentrate enough light to cause permanent damage. This gives Mercury a boundary in practice as well as in concept. It is near the source of sight and near the source of blindness. That boundary shaped history. Transits of Mercury, when the planet passes directly between Earth and the Sun and appears as a tiny black dot crossing the solar disk, required special equipment and careful timing. They occur only when Mercury is at inferior conjunction while also crossing the plane of Earth's orbit. Because Mercury's orbit is tilted by about 7 degrees relative to Earth's, most inferior conjunctions do not produce transits. The planet passes above or below the Sun from our perspective. Again, the sky withholds the simple event unless the geometry is exact. Transits helped astronomers measure and refine the scale of the solar system. They also made visible the fact that Mercury is truly a world between Earth and the Sun, not just a wandering point. But even then, the planet appears tiny. Against the solar disk, Mercury is a speck. Venus during transit looks larger and more dramatic. Mercury looks almost like a flaw in the light, yet that flaw is a planet. There is a recurring pattern here. Mercury appears as a speck, a mismatch, a small point, a tiny precession, a brief twilight object. Its significance hides under smallness. That is a useful antidote to the way we often imagine importance. The universe does not scale meaning according to visibility. A small angle can reveal a new theory. A small world can carry a large core. A small window after sunset can open into deep time. The ancient world did not have our categories, but it did have patience. Watching Mercury required knowing when to expect it. Its appearances were tied to calendars, omens, and cycles. People looked before dawn and after sunset because the planet belonged to those edges. They may not have known why it stayed near the sun, but they knew that it did. Accurate observation often begins before accurate explanation. This matters because modern science is sometimes presented as if it replaced wonder with instruments. In reality, instruments extend the same impulse. A spacecraft orbiting Mercury is a more elaborate form of looking. A gravity-assist trajectory is a more elaborate form of patience. A relativistic calculation is a more elaborate form of noticing that something does not quite fit. Mercury is therefore a bridge between naked eye wonder and high-precision physics. It is visible enough for ordinary people to seek, difficult enough to humble them, and scientifically rich enough to occupy experts for generations. Few objects hold all three roles so cleanly. The planet's color does not help it much. Mercury is not red like Mars or golden like Saturn in a telescope. It is gray and subdued with a low albedo, meaning it reflects only a modest fraction of the sunlight hitting it. Its apparent brightness comes from closeness to the sun in geometry more than from a reflective surface. The planet itself is dark compared with the glare around it. That darkness is interesting. Airless bodies are weathered by micrometeorites and the solar wind. Their surfaces change chemically and optically over time. Space weathering can darken and redden material, altering the way light reflects from grains of rock and dust. Mercury's surface has spent billions of years under intense bombardment by sunlight and particles. Its color is not merely an aesthetic fact, it is the surface record of exposure. The term space weather often makes people think of Earth, auroras, satellite risks, and solar storms. But Mercury experiences space weather without the cushioning Earth has. Its exosphere is continually replenished and altered. Sodium, potassium, calcium, and other atoms can be liberated from the surface. The planet's environment is a conversation between rock and solar wind. Earth's atmosphere makes us forget that surfaces can be directly exposed to space. On Mercury, there is no thick air to mediate the relationship. Sunlight, charged particles, micrometeorites, and thermal stress reach the ground with little interruption. The surface is not just sitting there, it is being processed. This is one reason Mercury is useful for understanding airless bodies. The Moon, asteroids, and many moons of outer planets have surfaces shaped by space exposure, but Mercury occupies an intense inner environment. It gives scientists a nearby laboratory for how materials behave under strong solar forcing. Even its magnetosphere behaves in a compressed way. Earth's magnetosphere stretches far into space, forming a long magnetotail away from the Sun. Mercury's magnetic bubble is small, sometimes so compressed by solar wind pressure that the interaction can bring charged particles close to the surface. The scale is different, but the physics connects Mercury to the broader study of plasma environments. Plasma is often called the fourth state of matter, a gas of charged particles whose behavior is shaped by electric and magnetic fields. The Sun releases plasma continuously as the solar wind. Planets with magnetic fields carve cavities in that flow. Mercury's cavity is small and dynamic, like a miniature version of a larger cosmic process. Studying it helps scientists understand how magnetic fields stand against stellar outflow. This matters beyond Mercury. Around other stars, planets close to their suns may endure powerful stellar winds and radiation. Whether a planet keeps an atmosphere can depend on magnetic fields, gravity, chemistry, and stellar activity. Mercury is not habitable, but its stripped environment helps us ask what close-in rocky planets become when a star dominates them. There is also the question of Mercury's interior. A large core implies a history of differentiation, when heavier materials sank inward and lighter silicates formed outer layers. But the exact size, state, and composition of that core remain important scientific questions. Messenger's gravity and magnetic data gave strong constraints. Bepi-Colombo is expected to improve them. A molten or partially molten outer core can support a dynamo, the process by which moving conductive fluid generates a magnetic field. Earth's dynamo is powered by heat flow, compositional convection, and rotation inside its iron-rich core. Mercury's dynamo is weaker and more puzzling, but the existence of a field tells us that the interior is not simply frozen metal. There is motion hidden below the cratered crust. Hidden motion is another Mercury theme. From outside, the planet looks dead. From the surface, nothing like wind or water moves. But below, metal may still flow. Around it, plasma streams and magnetic fields shift. In its orbit, the ellipse turns slowly through spacetime. Stillness is only a surface impression. Even the craters are not static in meaning. They are records of impact rates, surface ages, and geological resurfacing. Counting craters helps planetary scientists estimate relative ages. A heavily cratered region is usually older than a smoother volcanic plain because it has been exposed longer to impacts. Mercury's surface therefore becomes a clock, though a complicated one. The early solar system was more violent than the present one. Leftover planetesimals and debris struck growing planets and moons. Mercury's ancient crust preserves part of that bombardment history. Each crater is an event, but together they become statistics. From chaos, scientists extract chronology. That is another form of reading. Not reading words, but reading density, overlap, degradation, ejecta patterns, and relationships between features. The surface tells time in damage. Damage is not always loss in science. Damage can be data. A crater reveals the energy of an impact. A scarp reveals contraction. A basin reveals ancient catastrophe. A shadowed deposit reveals thermal history. Mercury's battered face is not a ruin of knowledge. It is the knowledge. This turns the planet into an archive without pages. The pages are rock, shadow, gravity, and light. Spacecraft translate them into maps and measurements, but the archive itself has been there all along, circling the sun every 88 days. When people ask why we study planets that seem lifeless, Mercury is one answer. Life is not the only reason a world matters. The planet can matter because it explains formation, gravity, magnetism, geology, stellar interaction, and the limits of our models. The universe is not valuable only where it resembles us. Mercury is valuable precisely because it does not resemble us. It shows what a rocky planet can be when stripped of comfort. It shows how much diversity exists among bodies made mostly of stone and metal. It reminds us that Earth is not the default rocky planet. Earth is one outcome. Mercury is another. In the evening sky, however, none of this announces itself. That is the quiet power of astronomy. The small visible thing is a handle attached to invisible depth. You pull on it with curiosity, and the whole machinery begins to come into view. The handle in June 2026 is greatest eastern elongation. It is a technical alignment, but it is also an invitation. It says, for once, this hidden planet is far enough from the sun's glare for human eyes to have a chance. Look quickly. Look carefully. Look low. And while you look, remember that the planet is not actually near the horizon. The horizon is Earth's local interruption. Mercury is in space, moving around the sun. What you see low in the sky is the intersection of its orbit with your evening, your latitude, your weather, and the turning of Earth beneath your feet. Every observation is local. Every conclusion must climb beyond the local. That is the movement of science. Mercury begins as a local glimmer and becomes a global map, then a heliocentric orbit, then a relativistic test, then a planetary system, then a clue to exoplanets. It expands as our questions expand. This expansion of meaning may be the most important part of the story. The universe does not become larger only when telescopes see farther. It also becomes larger when familiar objects become deeper. Mercury has been in the human sky since before history, yet it keeps becoming new. That is a hopeful thought for science. Discovery is not only finding what no one has seen. Sometimes discovery is seeing the known thing properly for the first time. Mercury was known as a wandering light, then as an inner planet, then as a difficult telescopic disk, then as a relativistic clue, then as a cratered spacecraft target, then as a world of ice, hollows, contraction, and magnetism. The same object kept changing because our understanding changed. The sky holds many such objects. The moon is familiar until you consider its formation. The sun is familiar until you consider nuclear fusion. The stars are familiar until you consider that they are suns across deep time. Familiarity is often just mystery we have stopped noticing. Mercury asks us to notice again. Maybe that is why a planet that is hard to see is worth seeking. The act of seeking interrupts the automatic sky. It makes you aware of the sun's path, the ecliptic, the horizon, the timing of twilight, the order of planets, and the fact that Earth itself is moving. Looking for Mercury turns the observer into part of the diagram. You are not outside the solar system looking down. You are inside it, standing on one moving planet, trying to see another moving planet near a star whose light is scattering through your atmosphere. That is what observation really is. It is participation. The solar system is not a model on a table. It is the place we are in. Mercury's low evening appearance makes that obvious because you can feel the limitations of your position. You cannot command the planet higher. You cannot darken the sky faster. You cannot remove the horizon. You can only understand the geometry and choose your moment. There is humility in choosing the moment rather than controlling the event. Science often works that way. Eclipses must be waited for. Transits must be predicted. Spacecraft flybys happen in brief windows after years of preparation. A gravitational wave passes through detectors in a fraction of a second. A supernova appears when a star ends itself, not when we request it. The universe offers windows. We build patience around them. Mercury's elongation is a small window, but it belongs to that larger pattern. It reminds us that timing is part of knowledge. It also reminds us that inner planets are not minor characters. Venus and Mercury are often overshadowed by Mars in human imagination because Mars seems reachable, visible, and possibly once habitable. But the inner planets are essential to understanding why habitability exists at all. Venus warns us about atmospheres and greenhouse physics. Mercury teaches us about formation extremes, solar exposure, and gravity. Near the Sun, Earth sits between lessons. We understand home by studying the neighbors that are not home. Mercury is the neighbor closest to the star. That closeness has consequences for everything. The planet's year, temperature, visibility, spacecraft access, space environment, and relativistic significance all flow from its position near the Sun. One fact branches into many. This branching is a good way to think about science storytelling. Start with one observation. Mercury is visible after sunset during greatest elongation. Ask why. The answer leads to inner orbits. Ask what Mercury is. The answer leads to metal cores and surface geology. Ask why its orbit mattered. The answer leads to general relativity. Ask how we know the surface. The answer leads to spacecraft navigation. Ask what remains unknown. The answer leads to Bepi-Colombo and future data. A single sky event becomes a map of connected ideas. That is why the planet deserves more than a calendar note. The evening of June 15th is not the whole story. It is the doorway. Beyond it is a planet that has spent billions of years close to overwhelming light, quietly holding clues in its motion and rock. And perhaps the most unsettling idea is this: Mercury did not become important when we noticed it. It was always tracing curved space-time. It always had its dense core. It always had its long, strange day. It always had its ice and shadow if the deposits were there before we knew them. Human knowledge arrived late. The universe does not wait for recognition. Our discoveries are not the beginning of truth. They are the moment truth becomes visible to us. Mercury has been near the Sun the whole time, appearing and disappearing in twilight for every generation that cared to look. The planet was never empty of meaning. We were only slow to read it. Tonight we followed Mercury from twilight into the machinery of the solar system, from an evening elongation to a planet of iron, ice, heat, resonance, spacecraft, and curved space-time. We began with a small point near sunset and ended with the realization that one of the hardest planets to see has been one of the most important planets to understand. The open question is not only how Mercury became the world it is how many other truths are sitting near the glare, present but unnoticed, waiting for someone to measure a small discrepancy and refuse to look away. Subscribe to Dark Matter Radio for more long-form science, and leave a comment with the question Mercury leaves in your mind. Until next time, keep looking into the dark.